Alright, this is a combination capacitor circuit. We can see we've got a 4 microfarad, 2 microfarad capacitor in parallel with each other, which is in turn in series with this 3 microfarad capacitor. What we need to do is calculate the potential difference or voltage across each capacitor and also the charge on each capacitor. We're going to use the capacitor concepts that those in series have the charge the same on each capacitor and the potential is different on each, but capacitors in parallel have the charge different on each and the potential is going to be the same on each different capacitor. So as we start framing up the problem, the first thing we need to do is find the equivalent capacitance of the circuit. It's easiest to work with the parallel branch first. We can see we've got in parallel the 4 microfarad and the 2 microfarad capacitor, and remember that that formula is just the sum of the two together. So we've got a total equivalency for the parallel branch of 6 microfarads. And what that allows us to do is redraw the circuit. That's the easiest thing to do right here, is go ahead and redraw the circuit so that we have a 6 microfarad equivalence in series with the 3 microfarad. Then what we do is we take that and we have to break it down even further, because those two now combine just like series capacitors would. So that's a 1 over, an inverse relationship. 1 over the capacitors in series is equivalent to the 1 over the 6 microfarad and 1 over the 3 microfarad. So doing the math, we see we would come up, when we go ahead and solve, that will be equivalent to a 2 microfarad capacitor. Okay, it's easiest then to visualize it by redrawing the entire capacitance as one single 2 microfarad capacitor attached to the 12 volts. And we can begin then by finding out what the charge would be on this kind of quasi 2 microfarad capacitor. Well, when we do that, then the next step is we have to work backwards. So using these concepts, we can go back to the drawing that we made here of a 6 microfarad and a 3 microfarad capacitor and work with these ideas right here. We know that the charge has to be the same on each, but the potential will be different on each as well. So knowing that this 24 microcoulomb charge would have to be the same on these plates right here, we can work with our capacitance formula and calculate the potential on each one. So knowing that the potential on the 6 microfarad one should be the charge on it divided by its capacitance, we'd get 24 microcoulombs divided by the 6 microfarads. That'll give us 4 volts across that one. And we would know that to get 12 volts, we're either going to have 8 volts on the other one, or you can do the calculation here across the 3 microfarad capacitor. 24 over 3 would give you the 8 volts. So we're almost there. We've fully analyzed the 3 microfarad capacitor, which was in our original circuit. But now what we got to do is break the 6 microfarad one back to its original capacitors that we have right here, the 4 microfarad and the 2 microfarad one. Well, that was a parallel arrangement. So we're going to go back and use the rules for parallel now on that one. And the rules for parallel tell us that the charge will be different on each one, but the potential across each has to be the same. And we saw up here that that's going to be 4 volts across this part of the circuit. So knowing that equivalency, we can go back and we just apply our capacitor formula to find the charge on each one then. So 4 microfarads times the 4 volts would give us a charge of 16 microcoulombs on the 4 microfarad capacitor. And coming on down, we would see on the 2 microfarad capacitor, the calculation will give us 8 microcoulombs, which adds up to our total of 24 microcoulombs of charge, right, on the whole thing. And that should be true because of charge conservation. And that takes care of a complete analysis of the formula, of the circuit.